Welcome back to the aromatic substitution reaction chapter. We're on 18.6 now. Now that we're outside of the reactions, we went over halogenation, sulfonation, nitration, Friedel-Crafts reactions, and those very niche reactions. We're now going to look at a very important concept of, okay, let's have another group on that aromatic before we do it. Either what we call activating or deactivating, and what will that do to the reactivity of the molecule? And is that going to direct our reactant to pick a spot on that aromatic ring in any way? First, we have what's called activating groups. Activating groups tend to usually be electron donating groups, meaning they donate electron density towards the aromatic ring and therefore adds energy to those aromatic pi electrons, right? And it's important. We're going to see this more in detail, but we call this these groups ortho-para directors, meaning if you remember, ortho means one away from a substituent, meta means two away, and then para just means all the way around, so three away. So we call that an ortho-para director. We'll see roughly, and now this is made up numbers, so don't take this very don't take this take this with a grain of salt. Basically, you're gonna get about 30% ortho, so one away. Para, you'll get about 70%, 69% is what I said, just to leave an extra percentage for meta, because you get very, very little meta with activating groups. I want to now show you something on my drawing software. So the first little concept I wanted to show you is the resonance structures here. So if I asked you what the major product of this reaction would be, what would you say? Well, you're going to get a mixture of products. You're going to get, hopefully you remember those percentages I gave you. If we have hydroxyl, a phenol in this case, if we have this phenol group, we'll see that if we just had excess of all of this, we might get this, right? This is just a visual representation. More realistically, you would get in either ortho position at about 30%, that's the times sign, Corbin, 30%, and then you'd also get this product here. Sorry, gotta go like this, OH, and then in the para position. So here you'd get about 69%. And then the more minute product would be adding in the meta position, which would be, I'll go back to my original molecule here, that would be adding here or here. So that's meta, and we don't get meta here. So how can we explain this? I want to just draw a resonance structure for you of phenol. I think that will help quite a bit in understanding why we get directionality. Alright, so if I have this phenol group here, and I asked you to draw all the resonance structures, well, here's what you'd probably do. So I'm going to use a fun color red to show the resonance arrows here. So let's just say, for example, that this hydroxyl group decides to make a pi bond in its resonance structure, and it does because resonance structures aren't really indicative of one singular molecule. It just helps us visualize what the molecule is doing and how we can identify partial charges. Okay, so we make a double bond here, or a double bond, C double bond O, and then this will cause these pi electrons to jump to this carbon here. And let me just draw that resonance form. We're going to get something that looks like this. Oops, can't draw today. We're going to get a negative charge here. Okay, and we're going to get that phenol group, or that hydroxy group, I should say. And oop, we don't have two, we have this, so that's positively charged. Now, this may be a little bit of a minor resonance contributor, but it's still there. So we have this one, and then this can form this one here, where these pi electrons will go like this, and we'll push these ones onto this carbon. Let me use a fun color. I'm feeling purple right now. Purple. Going to be pushed right here. Alright, so then we have a negative charge in Give me a second here. I'm going to draw this all in before I yap a little bit. And then we have those pi electrons, positive charge here in lone pairs. We're going to have a negative charge in the para position. So we had a negative charge in the ortho position, negative charge here, right? All right, and then for our final one, we'll go like this and put a negative charge on the other ortho position, and we get this here. So dual bond OH, and we get that negative charge. Very nice. Okay. So you can see the resonance structures here. We have this original phenol, basic, normal, and then we arrow push around, but we never see a negative charge on the meta position. And this is important, because if I were to draw out the hybrid of this, we might assume it would look something like this. So I'll just draw the skeletal carbons like this, right? And I'll draw that OH like that. Put some fun little blue electrons on that OH. So this position here, the ortho positions, let me just show the delocalization of those electrons all around the ring in conjugation with each other. This is partially negative, and there's some here too. Partial negative here, partial negative here. Oop, that's not good, delta. And we have in the para position, partial negative here. So if some atom, some electrophile was coming in to react, well, it's probably going to want to pick the spot that's more reactive, and that's going to be at these partially negative areas. So if I were that bromine, it would be through this FeBr, Br4. It's gonna, and then there's that Br here, right? That's gonna break this way, and some of these are gonna come out like this and steal that bromine, and that's the reaction we saw up here, right? That's what I'm trying to get at, right? So why we get that selectivity is directly because of this resonance structure having negative charges defined at certain points in the ortho and para position. Hopefully that makes sense. Okay, so another way we can visualize this, just to show you the reason we have these different percentages here, like we have that 1% for the meta product, about 70% for the para product, and 30% for the ortho product. We can explain this by showing the different attacks, quote unquote, hypothetically, to show what the resulting compound looks like. So let's draw this here. So if we were to do, let's add our hydroxy group here. If we were to do that halogenation with bromine gas and then our iron tribromide, right, and we were to say, okay, let's attack it in the ortho position. Ortho attack. So let's draw a structure where we have an ortho attack. Okay, we have our OH here. All right, and I don't want to show the full structure yet. Oops. And that would put a positive charge here. Okay, and then we have our bromine group here. So before any elimination happens, let's look at the resulting structure. So we have this compound here, and now let's draw the resonance forms of it. So these pi electrons go like that. I know this is going to be quite a pain, I know, but stay with me, everyone. We'll be just fine. We're going to have a positive charge here. And if we go like this, if we go like, it would be this here, we're going to get this molecule, this configuration, I should say. All right, so with the ortho attack, let's count. Let's do a little bit of counting. Our carbocations, how much of each did we make? So we made a tertiary carbocation, so I'll just draw a 3 degree here. And then we have a secondary and another secondary. Alrighty, and this is for an ortho attack. So I'll take note of that. We'll come back to this to kind of compare the positive charges. But when you draw these resonance forms, you need to look at the positive charges. So we have 1 really good carbocation and 2, you know, okay ones. All right, and that's for the ortho attack. Now let's move on to if we were to do. Let's go with para. We'll save meta for the last to make a point. So we have that BR2, FeBr2, or FrBr3, and we're gonna attach this in the para position. So we put that there. We're going to have a positive charge here. So we have a secondary one. Let's see here. So we can do, I'll do this one here. So we can do that. I'm going to draw this just so it's not such an eyesore. Okay, and then we have this structure here. And then alright, and we have our hydroxide group, and then this comes around like that. And that leaves us with this here. And a positive charge here. Alrighty. So let's count our carbocations. Right? So we have a secondary, tertiary, secondary. So same as the last one. We'll get into why those percentages are a little different in just a moment here, but I do want to draw meta before we do that, just so we can see the difference. Alright. Now for the final one, a meta attack. A meta attack. So if we attach it in the meta position, and yeah, that would be there. Alrighty, so we would attack these pi electrons, put the positive charge here. Pi bond, pi bond. Okay. Alright. This is quite the mouthful, I should say. So we do a meta attack here. We get we can push these pi electrons here, give us this compound, so that would put the positive charge here. And oh my goodness, why did I put it there? No. Sorry. We're going to push the electrons here. Like that. And that puts the positive charge there. Jeez Louise. I do not have it today, guys. And we put the bromine in. Okie dokie. And we get this here. And you probably see the problem here. I hope you see it. I mean, it's not the worst thing in the world to see, but who knows? Well, let's count our positive charges here. We have a secondary, secondary, secondary. So that's that's a difference I see. Secondary, secondary, secondary. All right, so let's first explain why. Like we said here, we're only going to get about 1% meta. Can we explain that through this here? So in our ortho substitution reaction, we get, in our resonance forms, we have a very stable tertiary carbocation and 2 relatively stable secondary carbocations. But if we go here, we have secondary, tertiary, secondary, right? Same thing. And that's for the para attack. But for meta, you'll see that we have secondary, secondary, secondary. And that means this compound is less stable and therefore less likely to form. The activation energy, if you were to look at the energy diagrams, you'd see this here. And we'll just compare the para one to meta. So if we looked at, and this is energy, and this is reaction coordinate. So if we're gonna say red is para, we'll see that the EA of the reaction is like that. But if we looked at meta, it would be something more like this. Takes a lot more energy, right? And that would be like this. So like that. So the activation energy of the meta is a lot more, and that is no bueno if we want the reaction to occur. So, all right, and the final point I wanted to make, this is the harder one, and I'm sorry if I didn't get to this right away. I just really wanted to save it for the last part, is why, if we have two ortho positions possible, why do we get double the amount of para? It feels a little backwards, right? So if we look at this, we have one, I'll just draw this again. If we look at benzene and we have some activating group, we have here two ortho positions on that molecule, right? But we only have one para, and yet it seems like we get double the amount of para, which is a little strange, isn't it? Well, you need to take into consideration the concept of steric interactions. That raises the activation energy of the reaction. If I attached, let me go back here, and let me draw in my pi electrons. If I added a group here, so we'll just say G for group. If I added a group here, there's going to be some steric interaction right there, and that's no good, right? That raises the activation energy of this molecule, or to form it, right? So because of that reason alone, there are other factors, but that's the easiest one to see. That's the reason para gets 2 times more, even though it might be a little backwards. Like if I put a group here, unless this molecule here is like throwing spitballs over to this this activating group, I don't really think there's any steric interaction there that's gonna hinder this molecule's energy of formation. So that was activating groups. There was a lot to say there, so I apologize if that video was kind of long. I hope you guys did enjoy, though. Check out the deactivating groups, which is going to be the next video in this series. Thank you so much for watching.